Hello and welcome to my NIM talk called arc/org. So this is a story about how I tried to replace NIM's garbage collector with reference counting, and later on I added a cycle collector, at which point it's a garbage collector, right? So I didn't plan it this way, but this is the story of how it came to be. We started with a question, can we bring more move semantics to NIM? Because move semantics are a success story for Rust and C++, and NIM faces the very same problems that these other systems programming languages do. For example, we have sequences, or in C++ called vectors, which are arrays that can grow. And how do you implement the memory management for these things? So here is a simple example. I start with a sequence that contains two numbers, and I append the number 3 to these numbers. And now what happens in memory? Let's assume that so this is how we start. We start with a sequence, and it's implemented with a length and a capacity, and we assume the capacity is just 2. So if we want to append a new number, we need to allocate a bigger block of memory for this data pointer and copy the elements over, and then append the 3, and then we have the old pointer left, and the question is what to do with it. Of course, what we want to do it is to free it immediately, because that's the best solution for the memory consumption of a program. So now here's the real problem. If we decide to free the pointer immediately, how do we deal with the fact that the pointer might have been copied? So in line 2 I say other is the same as some numbers, and if line 3 invalidates this pointer, other would contain a dangling pointer. So that's a bad solution. So there's the existing solution that NIM does is it does a deep copy for this assignment in line 2, much like C++ does it. But there are other solutions possible. For instance, you could say, well, let's implement the sequence as a pointer to a pointer, so by another indirection, and then we need to count the pointer somehow, or we need a tracing garbage collector to see if the pointer can be freed. That's basically C# and Java's solution. There is also, we can also say, okay, well, we don't allow this assignment in line 2 because it's kind of an expensive copy that we have to perform. Or finally we say, yeah, let's move these numbers to other. So that's available in today's NIM with this system.move operation. And after the move, the sum numbers is an empty sequence, and if we append the 3 to it, only the 3 will be inside the sequence. So that's an explicit move. It's kind of a destructive read, and we think it's okay because, well, you wrote the move on your own, so you are aware of what happens, and it's comparable to, say, some numbers.setLength or is 0, which is also an operation that we support, and nobody ever complained about it. More interestingly, though, is that moves also can happen implicitly if they are not dangerous. So first example here, the function result returns a new fresh value, and since we cannot observe this value otherwise, it's fine to move the f's result directly into the a without the copy. More generally, we can always move if the source isn't used afterwards anymore. So here's a different example. Again, we can move from G into named value, and since named value isn't used on this afterwards, we can move it into the F as well. And then we can move f's result into a. That's pretty neat. And here's a different example. So if I start with x and it has 3 numbers, and then I don't use the x after line 2 anymore, I can move it into the y. And likewise, I can move from y to z because y isn't used after line 3. So we can reason about locations in the compiler, and the problem now is that these locations are kind of limited to basically either it's a function, the result of a function call, or it's a local variable that we can analyze the control flow graph. So we need to help the compiler a little bit in other places. For instance, here, so this is a pseudocode for a hash table implementation, and the goal is to put a key value pair inside this table, and the value happens to be a sequence of strings, so it's potentially expensive to copy. And now that value is a parameter, we cannot say, yeah, it won't get used afterwards, after this call, we don't know. So we have to perform the copy in line 3, and that's not desirable. So sync parameters have been invented to prevent this. So if you annotate the parameter as a sync, then the compiler says, okay, the callee guarantees that the value is kind of fresh, won't be used afterwards. And so I can perform a move in line 3. And now this bubbles up the call chain, this requirement. And in line 6 we can say, oh, wait a second, values is passed to a sync parameter and values isn't used afterwards, so I can move it into the put operation, and inside put in line 3 it will get moved into this final position. Now, if I happen to use values afterwards, the compiler will say, yeah, this is not going to work out. I'm going to produce a copy of values because that can be synced into this put operation. But this is an implicit copy, so I'm telling you about it because maybe you want to restructure your program to avoid this copy. And indeed, in this case, we can restructure the program and say, okay, fair enough. How about we output the values first before we put it into the table, and then all the copies are gone. But of course, if this echo statement is only for debugging purposes, you don't care about these copies because this is just code that you wrote in a hurry. And you will remove this echo statement soon again afterwards. The corresponding problem, or the symmetric problem, is getting a value out of some container. Again, we have the pseudo hash table here, and the question is how to get the value that belongs to the key. So we hash the key into some integer value, and then we say, yeah, the value is supposed to be at t dot slots at h. And again, t dot slots at position h is a complex expression that the compiler cannot reason about, and it says, yeah, okay, this is probably not the last usage of this location, so it should be a copy here. And now if we say, yeah, we can move it, the compiler will tell us that no, actually you cannot move it, because move takes a var parameter, like it wants mutability, and the t isn't mutable here. Okay, so we say, so we add the mutability, but now we are aware that, wait a second, we are mutating this table for read access. This cannot be a good idea. So this would compile, but of course, like, you read the value once and afterwards it's gone. Pretty bad. So we need to be able to provide an immutable view into this v so that it is still kept in the table, but we don't have a copy. And that's achievable with this land return type. It's comparable to a var return type, which was already in nim version 1. Except that this land is now, as I said, it's an immutable view, so you cannot mutate the v. Okay, and with this we can eliminate basically all copies. Now, how it really works under the hood is via so-called hooks. So there are 3 hooks, like there's the move assignment operator, the assignment operator, and the destructor. And you can provide your own custom ones for, say, files or sockets. So as in other languages, they would get closed automatically at scope exit. So that's pretty nice. And we will see how this technology enables much better composition between these different memory management solutions and containers. That, much better composition than we had in NIM version 1. So I claim with these things we can write a sequence in NIM that works as the built-in sequence type. And here is how to do it. So as we start with a sequence of type T, and it has a length and a capacity, as you can see in line 3. And then we have a pointer to an unchecked array, which is the block of memory where the elements can be stored into. And the destructor is spelled in this backticks equals destroy. And what we need to do in destroy is we need to free the memory. That's done in line 9. But before we do that, we want to destroy every single element in the sequence as well. So that nesting a custom sequence in a custom sequence in a NIM sequence, so that it all works out, so that the nesting is done properly. And then we set the pointer to nil, so that if you call the destructor twice, nothing really happens. I mean, nothing bad happens. The assignment operator looks like this. So again, we want to perform the deep copy operation. So first of all, we want to say, is this a self-assignment? And if so, we don't have to do anything. But if not, we want to destroy A first, because it's there might be data inside the sequence already, and we have to free the memory, otherwise we would leak. And then we copy the length and the capacity over from B, and then we allocate a buffer that of the size that we wanted to have. And we copy the elements over in line 9 and 10. And again, here it uses the assignment operator that you can overwrite in your custom types. So again, this sequence works with any NIM type that you can come up with. The move operator is called a sync, and it's a specialty in NIM that it actually only does half of the move operation. Namely, it does the stealing of the guts of the B vector. It's done in line 5, 6, and 7. But the interesting thing here is that B isn't reset to nil, like B.data isn't set to nil afterwards. In C++ that would be the case. But here we say, it's the sync that we need to know about, and if B is used, could be used afterwards, we will inject these statements like B data is set to nil. But what happens very often is that we know statically that B isn't used afterwards, so there is no need to destroy it, nor to set the pointer to nil, because these would be just writes to the stack that are, and the stack frame is about to disappear anyhow, so kind of like that. So that's a pretty good optimization. So this is the memory management part of the custom sequence, and of course you can do more than just allocating memory. You can access the elements and you can append to this vector. So in line 1 I say here's how to add the T to my sequence of T, and the Y here should be a sync parameter because we want to take over the value and embed it into our container. So again, line 3, this assignment is actually a move. And in line 6, we say, okay, you want to get a T out of this sequence. So we borrow it like with this length T annotation, and since it's a length assignment in line 8, again, there's no copy. And it's just like in nim version 1, there is a mutable view into this data, but if I want the mutable view, the sequence itself must have been mutable. So that's why there is a var my sequence in line 10. And again, the var result produces no copy. And there is this override assignment at position I operation in line 14. And again, it takes a y, and the y should be a sync. And yeah, these sync and length annotations are optimizations. So if you write the code without these, it still works, except that it will run a bit slower. So now that we have seen how moves help for our custom container types, and by optimizing assignments, we can apply this knowledge to nim's ref type. So how about we reference count nim instead of using a tracing gauge collector? So the this is what led to this GC::arc mode. So here is the real implementation of arc. So now it's not a sequence anymore, but a ref T, and it has a destructor, and the destructor, well, it has access to a ref count called RC. And if the ref count is 0, we say, yeah, you can deallocate the memory. And if not, you decrement the counter by 1. Pretty standard stuff. The assignment must say, wait a second, so B is now referred to once more than previously, if it's not nil. And the old A must be destroyed, and then A is equal to B. So this, and the sync here is a bit better to optimize. So we say, okay, B, we take over the B's reference count, because B won't be used afterwards anyhow. So we only need to copy the pointer in line 16, and before we can do that, we must destroy what was inside A. So that's arc. And now we have a new memory management mode for the nim compiler, and we can run a benchmark on it to see how it works, how well it works. So this is the classic binary tree benchmark. So we have a node with 2 children inside. There is some code checking that the tree was constructed correctly, and we have in line 11 we have a make tree function that can produce nodes up to some depth. So the benchmark is mostly about how fast can you allocate and deallocate memory. And this is the main thing. So we have some depth that we take from the command line arguments, and then we create long-lived trees and short-lived trees. Yeah, pretty boilerplate heavy stuff here. So these are the results. Arc beats all of our old garbage collectors by quite a bit, as you can see. So the Bohm garbage collector used to be the best for this benchmark. In fact, I tried for years to beat Bohm on this benchmark with our mark and sweep or deferred ref counting garbage collectors, and I couldn't make it. But with arc, no problem. 6.75 seconds compared to 12 seconds. Memory consumption is comparable. It's just that I cannot really access this peak memory as easily with Bohm as I can do that for the other garbage collectors. So, and the standard gauge collector is the deferred ref counting gauge collector. So it's 16 seconds, so it's quite a bit slower than Bohm. So yeah, over a factor of 2 faster than the default gauge collector. Now to see how much room there still is left, let's compare it to manual memory management, which is also, I mean, it has been possible in NIM for ages, except that maybe not many really know how it works. But you replace the ref by a PTR, which is an unchecked pointer in NIM. And then the code basically is the same, except that the construction now is more messy with this alloc and the cast statement in line 12. And of course we need to free the memory on our own, like the tree structure in line 19 to 21. So, and we need to insert these 3 tree calls into our program, and thankfully it's a micro benchmark, and usually micro benchmarks are easy to annotate with this lifetime information. All right. And we can see that unfortunately manual memory management is quite faster still. However, after an analysis, it turns out that most of the speed up is actually caused by the fact that that this node declaration here lacks the reference count field, and if I use a ref object, I have an implicitly declared reference count. So that's one machine word more that has to be written to for initialization, and that's what makes most of the difference. So if I add this reference count field to this node structure, the time changes to 6.2 seconds for manual memory management compared to 6.75 for ARC. So that's a pretty good result. And of course ARC can be optimized further still. So if for this particular benchmark I claim I can get the overhead down to 0. But of course it's a micro benchmark, so don't expect too much in the real world. When maybe your code does more than just blind allocations and deallocations. Anyhow, there is a different benchmark about latency. So this was also some kind of a standard benchmark a couple of years ago, and we had very, very good numbers already with this deferred ref counting soft real-time garbage collector that NIM offers. But again, ARC is better by a factor of 3 in this test. The total runtime of the benchmark is also down from 0.3 seconds to 0.2 seconds, and the peak memory consumption is also lower. So again, it wins in throughput and latency and memory consumption. So these destructors and moves and assignments can also do the famous technique for speeding up allocations further, which is called object pooling, or I think sometimes it's also called a memory region, or plenty of names for this idea. So instead of managing a single node in memory, we manage a pool of these nodes, and this is an outline of how you can do it. Well, actually it's a full program, but you're not supposed to understand every single line in there. So then you are on your own. You need to write an allocator that can return these nodes from the pool. And as you can see, there is some logic involved here, how to size the capacity so that we end up with a good runtime. So this was tuned for this benchmark. And here we can say, okay, I don't want to copy a pool accidentally at all. So I say the assignment operator is an error, so do not use it. And the destructor goes through this list of memory blocks and frees everything. And here is the assumption that the node itself doesn't have a destructor, so it's not even called. But you can easily write the destructor call here, and it will be optimized out if there is not, if it's like a blob of memory that doesn't have a custom destructor, and that's actually a library available in NimFusion, but when I wrote this code it wasn't there, so I had to write it on my own. So, and check tree remains. Make tree now gets this lovely pool parameter because we can only ask for new nodes from the pool. And since the pool is freed automatically for us, there is no need to free the memory in the program, but there's still the need now to actually declare these pools in the proper scope. So we have a long-lived pool in line 5 that will be destroyed at the end of main. And we have a short-lived pool in line 14 that will be destroyed for every iteration of the loop. But thanks to this lexical scoping, it's still, you cannot get it wrong, really. Okay, and the numbers change to 2.4 seconds now. So that's a very good result, again enabled by these custom destructors and assignment and moves. So that's a very good result, really. Like, it's again a factor of 2. And now compare 16 seconds to 2.4 seconds with the pooling. It's a difference between night and day. Okay, but so this led to ARC, but it's well known that reference counting cannot deal with cycles. And we have in them async, and async is based on callbacks, which have closures and on closure iterators, and you nest them, and it's basically like, I mean, we tried for months. It's just crazy. And so to break up these cycles, we need some algorithm. So here is the simple cycle. So A refers to B, and B refers to C, and C refers back to A. And we have a root pointing to A, so A's reference count is 2, and the other nodes have 1. So now let's assume the root disappears. A is back to A's reference count is 1, B's is 1, C's is 1. Yet, so we have a garbage cycle, yet those mechanisms don't work, so it's not freed. We leak this cycle. And now if you stare for this graph for a bit longer, you can see that this garbage cycle can be detected at runtime, because look, if you look at the sum of the reference counts, it's 3, and all the edges are 3 as well. So if these numbers are the same, you know it's a garbage cycle that you can free. So that's one heuristic how to deal with this problem. And of course the real algorithm is more advanced, but the point is the reference count information helps us to determine the dead cycles as well. So reference counting helps for the full garbage collection problem. So again, disappears, and now what R pointed to is kind of a candidate for a cycle check. So this led to org. All that's really changed here is if we deallocate the pointer, like if the reference count doesn't go to 0, we know there is something interesting going on, so we remember this X as a cycle candidate. And once we have collected many of these cycle candidates, we would run a tracing step to see if they are actually involved in a real cycle that is dead. And then we can free the cycle, so that's org. And we can compare this to the other memory management. So this is a different benchmark. This is Havluck, and it was designed to test for these cycle collectors, like how good they are. And in theory, since if you create too many cycles and you run the cycle collector too frequently, mark and sweep garbage collector wins against this strategy. But in this case, again, ARC is very good, or ARC in this case beats Boehm's garbage collector by quite something. I mean, it's not a factor of 2, but it's good. However, we compare it to ARC, which simply cannot free these cycles, and ARC is much faster still. So then the question was, how much of this overhead is caused by the fact that ARC actually collects the memory and ARC doesn't? Because, I mean, peak memory is one number, but the other number is how much bytes are left at the program, like how, at the end of the program when you need to collect all of them. And in ARC it's 0 because it collects everything, and in ARC it's basically the same number, like these 180 megabytes, because it cannot free these. So the question is maybe the overhead of ARC is just caused by this free that can happen and ARC simply cannot figure out. And it turns out that's not true, because we can we played with this benchmark and inserted some cycle breaking logic so that ARC can also free these. And then ARC is at 0.39 or at 0.4 seconds. So it's still significantly faster than ARC. So these cycle candidates and these tracing of these potential garbage cycles, it really does cost us runtime. And we really want a mechanism to help the memory system. So this is the Acyclic pragma. It's in NIM version 1, except that the garbage collectors in NIM version 1 ignore this pragma. Now it's back, it's alive again, and you can use it to speed up your code. So in this example here, this is again the binary tree. We want to tell the GC-ARC mechanism that, yeah, we do have cycles in the program, but not in this particular case. This is just a tree, so it's acyclic. Please deal with this. Consider it. And if you do that and use ARC with this binary tree, the runtime is essentially is exactly the same as ARC, because then we have all the knowledge that we need to avoid the overhead of the cycle collector. There is a different annotation that is new, and that's called a cursor. So assuming that we really only want the cycle collector as a last resort, we want to be able to write linked lists, and we say, look, a linked list is still acyclic. It has a next and a previous pointer, and the next one is kind of owning the object that comes afterwards, but the previous is a back reference, and so it shouldn't own the data. And that's what the cursor says. It's just a cursor into the data. Don't ref count it. So again, you can free the linked list after like the last scope is done with this list. And we have a data because yeah. So this is the cursor annotation. It's also useful for some other related problem, and that is, say you have this linked list and you want to search for a value, so contains, does this value exist on the list or not? And here is the traditional iteration loop, like it is a head, and while it isn't nil, proceed to the next element. In line 5 it becomes it.next. And without the cursor annotation, this would now produce reference count operations, because look, it's an assignment, it's a head, it's an expensive assignment because head isn't a sync parameter, and you cannot make it a sync parameter because you're not supposed, you do not want to take ownership of this list. So yeah, by annotating this as a cursor, you tell the system, yeah, this is used for iterating through the list, but it doesn't change the ownership involved. So you can optimize. Please don't insert these ref count operations. And this is the first and only annotation that is actually dangerous, because if you now it avoids the ref counting, but if you have some crazy logic where you iterate over this list while some other thing also mutates the list, then this will cause trouble. So yeah, beware with this cursor pragma. However, if you think about it, if you iterate over the list and mutate it, let's say even in some other thread, concurrently, then the fact that this lacks the reference count operations doesn't really matter, because even with the reference count operations, probably this would be a buggy program, because you don't use atomic assignments in there anyhow. So you're not making it worse with this cursor annotation, really. It's just you find your bugs earlier, because it's broken in a more obvious way then. All right. So now this is the state of the art, the development. We have this GC.org. To use it, I mean, GC.org is coming in NIM version 1.4. To use it, compile your programs with it, and then benchmark your program, and use these new lovely annotations like sync parameters, length return types. But best optimization is Acyclic, because it's not just a micro optimization. It's really changing the algorithm behind it. And beware with the cursor annotation, because that's the dangerous one. Yeah, but the other three, like if you use acyclic and it's actually cyclic, you leak memory, okay, but nothing worse happens. If you use length return types and it's not really a length, again, you lose performance. Same for sync. So don't just write them everywhere. You need to write them where they make sense, unfortunately. However, we also have sync parameter inference, and that's also shipping with 1.2, I think, but at least in 1.4. And yeah, we are also working on length inference. However, inferring that the type is really acyclic, even though it looks cyclic, is basically impossible given NIM's type design. So the acyclic annotation is really the most important thing to do. So yeah, more philosophically, NIM 1.4 is about declaratively describing how your program is structured, by describing the real topology. Like, is this, I mean, it looks like a graph, but what is it? Is it just a tree? Does it have back references? If so, where are they? And we use these declarative mechanism to get much more performance out of your program. But in my opinion, it's not only about performance, it's also helping the reader of your code. So if you know that you actually really only have a tree in your program, your fellow programmer can see, okay, this is a tree, how to traverse it. It's obvious that I don't have to have a set of where I remember where I've been before to avoid cycles, because it's just a tree and not some more general graph. Yeah, these destructors, assignment and things, they work under the hood. I mean, you don't have to use them, but they allow you to merge these ideas of automatic memory management with manual memory management. So, and this, finally, the benefit is that we can handle a shared heap with this. So atomic reference counting can be implemented with these hooks, and in fact NimFusion will have it. So yeah, thank you for your attention, and now I will try to answer all your questions.